So continuing from the last video, let me show you yet another way that we can calculate the equation of motion, this time using the equation for torque about the center of mass of the rigid body. So that's given as follows. That's equal to the moment of inertia about the center of mass times the angular acceleration of the frame of the rigid body, which is B, with respect to frame A. So we can, first let's define the terms or write down the terms that we know. We know from one of the prior videos that the moment of inertia of this disk about its center of mass is equal to m over 8 capital D squared plus little d squared. And the angular acceleration of B and A is equal to theta double dot B3. So now we just need to get this torque about the center of mass, right? Okay, so there's three forces that are acting upon this body, right? So there's one that's acting right at the center of mass, and then there's two that are acting at point O. So to be very thorough, what you could write is you can write out all of these forces. So if we wanted to look at include the force that's acting at the center of mass, we'd have the position vector from the center of mass to the center of the mass crossed with mg a1 plus the position vector from our center of mass to point O crossed with, in this case, we have F1 acting in the B1 direction plus F2 in the B2 direction. Now, I'm doing this for completeness, but it should be quite obvious that this here is going to go to 0, right? Applying a force at the point at which you're taking the torque about does not result in a torque, so that goes to 0. So we can simply, so I'm just going to erase this just for space purposes and write this again as R CB to O cross with our forces acting upon point O, which is F1 B1 plus F2 B2. So now we calculate out this cross product. And so our CB to point O is equal to D over 2, technically negative D2 B1, so crossed with F1 B1, right? So that's going to go to 0, you know. And then we have minus D over 2 B1 crossed with F2 B2. So that gives us the torque is equal to negative D F2 over 2 B3. And then if we write this equation out up here, I'll just write it down below actually here. So we get, so let's plug in all of these terms here. So our torque is negative dF2 over 2 B3, which is equal to m over 8 d squared plus little d squared times theta double dot B3. And so we can get rid of this B3 term. And so now what we're left with is, this I'll write up here, we have m over 8 d squared plus little d squared theta double dot plus F2, and then we have d. We can actually get rid of this 2, make that a 4. All right, so this becomes 4 equals 0. Now you can see that we actually have 2 unknowns. We don't know what F2 is, and we have our theta double dot term. So it turns out if we're going to use this method, we actually have to go ahead and use the forced linear momentum method to get an equation for F2 so that we can get rid of it. But that's okay for this purposes because I will show you how to use the forced linear momentum method here. Okay, so I'm just going to highlight this equation here, and I'm going to clear some space so that we can get the use the forced linear momentum method. So now that we've got our equation over here from our torque method, let's now use our force method so we can get rid of that F2 term. So we'll start by writing what we ultimately want, which is that our total force is equal to mass times the acceleration of the center of mass in frame A. So let's start by writing the position of the center of mass in frame A. That's going to equal d over 2 in B1. And we have the velocity of our center of mass. I'm going to go through this quickly because this should become almost, or should be old hat by now. So this gives us d theta over 2 times B2, which then gives us acceleration of the center of mass in frame A is going to be d theta double dot over 2 B2 minus d theta squared over 2 B1. So next we have to calculate our force vector that's acting upon our body. So we got 3 forces. We have F1 in the B1 direction plus F2 in the B2 direction. Plus we have mg acting in the A1 direction. Now you know that we're ultimately going to equate these, and it looks like we have mostly B terms. So let's turn this A1 into terms of B1 and B2. So we can write this as F. Now we have B1 plus F2 B2 plus mg, and this is going to be cosine theta B1 minus sine theta B2. And so now we equate the force and acceleration times mass. So what we get is F1, and I'm going to group the terms so that it's easier to see. We end up getting F1 plus mg cosine theta B1 plus F2 minus mg sine theta B2 is going to equal, we have m d theta double dot over 2 B2 minus m d theta dot squared over 2 B1. So if you equate these, the B1 and the B2 terms, you get B1 is equal to F1 plus mg cosine theta is equal to negative md theta dot squared over 2. And you get that B2 is equal to F2 minus mg sine theta, which is equal to md theta double dot over 2. All Right, and so all we need is one equation that gets rid of F2, so we can use this equation here. So we'll just simply rewrite that as F2 is equal to md theta double dot over 2 plus mg sine theta. So now let's plug that in to the equation that we got for torque. So we have m over 4 capital D squared, little d squared, theta double dot. And now we have our F2 terms. So now we have md squared theta double dot over 2. Remember, you're just multiplying these by a d, plus mgd sine theta equals 0. Well, we can write this middle term here. We can put this over 4 and write this as a 2. And we can combine these, so that ends up giving us m3d plus little d squared theta double dot over 4 plus mg d sine theta equals 0. And we can get rid of the m's on both sides. And now we are left with the exact same equation of motion that we calculated using the instantaneous center of rotation. Now, one key difference, of course, using this method, using the torque about the center of mass equation, is that these F1 and F2 forces drawn here we had to account for them, right? When we took the torque about the instantaneous center of rotation, right, so about this point here, we didn't have to care about those forces. We only had to deal with the effect of gravity. And that's why we only needed that one equation there. Whereas in this method, right, because F1 and or in this case, F2 showed up in our equation, we had to actually consider, we had to solve for it, right? F1 didn't show up because technically, right, if this is your center of mass here, F1 is acting in the direction of our center of mass, and so it's not producing a torque. And so for the last video, I'm actually going to show you how you can still use the conservation of energy method as well when you're calculating equations of motion for a rigid body.